All right, so we have some consequences of the theorem. So suppose f prime change its sign. So we have a graph of f prime. Suppose it change its sign from positive to negative, like this, at some point. From the previous theorem, we see if f prime is positive, your function is increasing, like this. And then if f prime is negative, it's decreasing like this. So what can you say? Once f prime changes sign from positive to negative, at some point C, then f has local maximum. Similarly, if f prime changes sign from negative to positive, then f must be decreasing, like this, and then positive f prime says that your f must be increasing like this. So we have local minimum. So if your f prime changes sign from negative to positive, then your function has local minimum. So that is our first derivative test. So sign of f prime tells you where your original function has local maximum and minimum. Second derivative test is also good consequence, very useful consequence from the theorem. Suppose your function has zero derivative, so it has either like this or that. So in order to have zero derivative, tangent lines must be horizontal like this. If f double prime is positive, then concave up. So zero derivative or horizontal tangent line together with concave up, together with concavity, gives you local minimum. So then once you combine those two conditions, we have local minimum. And if your f double prime is negative, then our function is concave downward. This concavity together with the horizontal tangent line tells you there is local maximum. So let us use those two tests. You can use any one of them, but remember, you need to check the sign of f prime or f double prime together with zero derivative. So here is a quick example where we can apply first and second derivative test to find local maximum minimum of given function. To use first or second derivative test, we need to take derivative, of course. So derivative is 3x squared. The first term gives you 3x squared and then minus 3. We need to know where it becomes 0, so we need to factor like this. We have 1 and negative 1. So we have 2 points, 1 and negative 1. Sorry, 1 and negative 1. So if you plot the graph of f prime, well, it's just a quadratic function with 2 x-intercepts. So we have graph like that, negative 1, 1. We have sign plus, minus, and then plus. So first derivative test says that whenever f prime changes its sign from positive to negative, your original function must be increasing and then decreasing. So your function has to have local maximum. Similarly, if your f prime change its sign from negative to positive, your original function must be decreasing and then increasing. So local minimum there. So first derivative test. F prime changes the sign from positive to negative at x equals -1. So that means f has local maximum at x equals -1. Similarly, f prime change its sign from negative to positive at 1. That's why f has local minimum at x equals 1. If you want, you can use second derivative test. For the second derivative test, you take second derivative is derivative of this 6x. So for the second derivative test, you combine condition where f prime becomes 0, and then you check the sign of this guy. So at x equals -1, f prime is 0, and f double prime. If you plug in -1, this sign is negative. Oops. You combine those two. So horizontal tangent line with concave downward. That means local maximum. F has local maximum. Similarly, at x equals 1, you combine horizontal tangent line with the sign. Horizontal tangent line and this positive sign. So positive sign tells you your function is concave upward, and then horizontal tangent line. So we have local minimum. So either first test or second test works, but you need to check the sign of f prime or f double prime.